Good morning again and welcome. Today is April 27th. We have quite a few materials to cover. We have chapters 16, 17, 18, and 19 before we are ready for the next exam. Chapters 14 and 15, we already covered them before exam 2. We are scheduled for exam 3 supposedly next week. I don't think that we're going to be ready for it next week, honestly, because of the fact that we have to be done by chapter 19 by then, be done completely with chemistry, and then we enter into geology. Since geology is a separate topic, that's what the exam 3 is supposed to cover, only basically the chemistry part of it. So what I'm suggesting is the exam has to be moved from next week to the week after. So exam 3 is not going to be happening on the week of, what is next week? It's the first week of May, but it's going to be rather happening on the second week of May, okay? And hopefully by then we would have covered at least to the end of chapter 19. That way we will be ready for exam 3, and in which case we'll be left just with the elements of basically geology and astronomy, which is going to be covered with exam 4. So this is basically how the thing is laid out at this point, okay? Does this make sense to you guys, at least the ones who are here right now? And I know a lot of you have joined us now. Okay, very good. Okay, so, okay, very good. So let me share the screen with you. So again, we covered chapters 14 and 15, and now we're continuing with the second part of the, or at least the third part actually of the course, which deals with the chemistry part of it. And we're dealing actually with mixtures in this topic. We will understand that basically most materials are mixtures. I mean, pure materials are the exception. And then also how matter is classified in terms of its structure. And we're going to describe solutions and solubility. Okay, basically when you take an element, for example, or a material, and you put it in a different material, and then it looks like the mixture now becomes more homogeneous. It looks like it's one basically element. In this case, you have a solution. Okay. How much of that solute inside that basically solvent is what is known as the solubility in this case, or the concentration, okay? We'll find different ways of expressing this concentration, whether in grams per liter or in parts per million, basically, or actually moles per liter, per whatever concentration in here volume that we're going to be accounting for. So again, we're going to talk about soaps and detergents and how they work in removing basically grime. And in that soaps, they have two components to them. They have a polar component that is attracted to water and a non-polar component that is attracted to grime. And together, they basically lift that dirt, if you wish, from a surface and basically dispose of it. So that's basically the concept of it. And then we're going to talk also about hard water and how to soften it. And the purification of water, which is a big industry and a very important one. And why is there a complaint in here about this? Okay, it doesn't matter. Okay, probably there is an extra space in here or something. Anyway, purification of water and waste treatment. So that's basically what this chapter is. Again, all of this has to do basically with mixture, because even when you're talking about waste treatment, basically how can you reverse the process basically of a solution in this case. So you have water that has impurities in it, and you would want to make it into a purified version of water that hopefully you can use everywhere water is needed, whether for drinking or for basically whatever uses you have in mind. Again, pure materials consisting only of one element or compound, those are usually represented by the periodic table elements. Mixture is a collection of two or more substances, okay? They don't necessarily have to have really chemical bond, but as long as you cannot, as long as the mixture is homogeneous and you cannot see the difference between that, that is basically what the mixture is. But most of the time, it requires actually some sort of a chemical bonding between them. Okay, and then can be separated to by physical means. So that's basically what the whole point in here is. Case in point, for example, you have coffee, which is already a mixture of different stuff in it, water and other materials in it. And then you add to it sugar, in which case that also becomes a homogeneous mixture. How do we know that? Because if I add sugar to it, if I taste it before adding the sugar to it, it has a certain taste. If I add sugar to it, I will notice that it becomes sweeter and sweeter, although the sugar appears to be going disappear basically in the solution. So what's going on in this case, you have the crystals of the sugar basically being broken. Usually you need some sort of a stirring to help it with the process of dissolving it into the coffee. So you break basically that crystalline structure for the sugar, and now you have a different structure between mainly water, which is a polar molecule, and the sugar in this case, and it's going to be distributed uniformly throughout the solution. And that is actually what you taste, okay? So this is basically in a nutshell what this whole topic is all about, okay? Again, you have pure elements or pure compounds in here. They have salt, for example, it's still pure if it does not have anything but NaCl in it. So it's not necessarily it has to be part of the periodic table. What you have in the periodic table, you have sodium by itself and chlorine by itself. But when you have this structure in here, this entire molecule sitting by itself, then as long as you don't have any impurities in it, this is actually still pure. The same thing with carbon dioxide and ammonia. But these elements in here, whether they are in pure structure like gold or, for example, sulfur or nitrogen molecules, in this case, it's still pure elements as long as you don't have anything in it. Now, again, in pure mixtures, they are divided into two types, homogeneous and then heterogeneous mixture. Homogeneous is basically when you have uniformity throughout. You cannot tell the difference. For example, when you look at the air surrounding you right now, you cannot see a separation between where the oxygen molecules are and where the nitrogen molecules are. They come together and it becomes just one unit. For you, you treat it as just one unit called air, albeit you can, the different molecules are actually separate and they're moving in every which way, but at any given volume of it, it's the same concentration of either, okay, the same proportions of either, okay, in the mixture. Same thing with salt water. Salt water, for example, in ocean, throughout the entire ocean, you have roughly the same concentration of salt throughout the entire ocean. So the same thing in here applies for white gold, for example, okay? But you also have suspensions like, for example, proteins in water or in blood or in milk or in fog. So that is actually also some sort of a homogeneous structure because it's distributed uniformly throughout. In this case, you have solution and suspension. Both of them are examples of homogeneous structure. A heterogeneous structure is sand in water. There is a clear separation between the two. As a matter of fact, you have two different phases. One of them is solid and the other one is liquid. Oil and water, they separate. Even though you try to mix them and you stir them together, if you wait a little later, you will see the separation between the two. Same phase, both of them are liquids, but you can see clearly where the first one is and where the second is. And even if you don't stir, I mean, even while you're stirring, you can still see different basically solutions in there. Again, salt and sand, you can clearly see the difference between them, and there are physical properties that distinguish one from the other, okay? So those are the main form of matter and how it presents itself to us. This is actually the exception to the rule, okay? Again, pure materials consists of a single element or a compound, as long as it's one, okay? Impure materials consists of two or more elements or compounds, okay? So those are the definitions that we're going with. Mixture may be heterogeneous or homogeneous. Homogeneous mixture or non-homogeneous mixture. So that's one of the two, one or the other. In a heterogeneous mixture, the different components can be seen as individual substances. You can actually see them yourself. Okay. In homogeneous mixtures, the composition throughout is the same throughout. So that is basically some of the basic definitions. Here are examples of heterogeneous mixtures. I mean, if you look, for example, in the pizza or this rock, you can clearly see the different colors and the different shapes and the different structures and the difference, even physical properties, hardness, and different stuff with it. Same thing with this one. This, all of them. Ignore the balloons for right now. We're looking at the air. We're not for. Don't think about the. So again, in this case, the homogeneous because you have in this case mainly oxygen and nitrogen in the air. Okay. Same thing with seawater. It has salt in it actually. And for you, it looks the same every which way. And the same thing, white gold, which is a combination of palladium and gold itself, okay? So again, heterogeneous mixtures, all components in the same, homogeneous, I'm sorry, mixture, all components are in the same phase, okay? So what happened in the case of salt inside the coffee is that salt inside the coffee, that's bad, okay, don't do it, okay? Sugar in the coffee is that the sugar in this case will actually become bind to the, so basically the solid structure that you have in there is broken, the crystalline structure is broken, and then the water becomes suspended the salt becomes sugar becomes suspended in the water, and then it takes its phase. Basically, it becomes also liquid. Okay. Suspension, different components in phases. Okay, like for example, it's not really suspended. It actually binds chemically to it. In this case, suspension, like for example, dirt inside water that you can clearly see, that is suspension. Okay. You have different phases actually. Hopefully you guys can go through these examples in here. A homogeneous mixture consisting of ions or molecules. Solvent, there are two kinds of things in here in a solution. There is a solvent and solute. Solvent is the main component of a solution. And the other one is the solute. It's the minor component of a solution. Case in point, for example, which one is a solvent, which one is the solute. In the case of sugar and coffee, of course, it's obvious in this case, the coffee, which is a mixture mainly of water, really. Water, which is really the solvent in this case. Okay. So probably I should stop using the word coffee. I should just use the word water with the sugar in it or salt in it. So in this case, I would be safe if I use water. Again, when you're starting adding solute inside the solvent, what happened in this case, at some point, you will reach a point where the minute you add the next one, you will start to see, in this case, there is a deposition. You will see actually that instead of going and mixing with the solvent, it's actually going to go to the bottom and rests. So in this case, we say we have reached the saturation point. You cannot add no more. Everywhere where the solvent can take has already taken and no more. So in that point, you have reached the saturation point. Okay. So the measure for this for how much concentrate for how much basically of a solute you have inside the solution in this case is the concentration. So that is basically how much can you put in before you start to see those basically solute deposit in the bottom of the or suspended or something. You see the different phases in it. Okay. So the concentration is solute over solution. If the solute is too high, then in this case it's concentrated. So that is again the definition in here. Otherwise it's dilute. Okay, so those are terms used in here depending on the value of the concentration. Again, we can use Avogadro's number, or we can use actually the moles, and we know that in 1 mole we have this many basically atoms inside a mole. So for example, if you look at the periodic table, the mass listed in there, the mass number listed in there, for example, hydrogen, it's 1. That means it's 1 gram per mole. If you take 1 gram of hydrogen and count basically how many hydrogen atoms are in that gram, you should find this many, which is Avogadro's number. So that is really the definition of the mole. If you take helium, for example, and you see the periodic table, it tells you it's 2. That means 2 grams will contain the same number as much as 1 gram of hydrogen, and so on and so forth. For example, if you look at carbon, it says 12. That means 12 grams for carbon will have this many atoms in it. 12 grams of carbon versus 1 gram of hydrogen will have the same number. So if you happen to have 12 grams of, 1 gram of oxygen and 1 gram of hydrogen, 1 gram of hydrogen will have far more atoms of hydrogen versus that of carbon. And same thing for oxygen, 16 and so on and so forth, nitrogen 14, and that is how the periodic table is giving you those numbers. So it's a useful number in here to use. So the formula mass of a substance expressed in grams contains 1 mole. So that is the rule for the periodic table. And this is the example I was talking about in here. Now, what I was mentioning in the beginning is actually the atoms. But for example, the oxygen atom itself is 16, but the molecule itself is an O2. It requires 2 of them together. 2 times 16 is actually 32 grams. That means 32 grams of air, oxygen, the one that we breathe, is actually have that many number, 6.02 times 10 to the power 23 of these molecules, okay? Carbon dioxide will have 12 for carbon and 2 times 16 for oxygen. That's a total of 32 plus 12, which is 44 grams. That means 44 grams of carbon dioxide will have the same number of 32 grams of oxygen molecule. Both of them have Avogadro's number. Sucrose, on the other hand, which is really the regular sugar that we have that we put in our coffee, has this many. 12 times 12, that's 144. 22 times 1, that is 22. 144 plus 22, that's 146, 166, probably. Plus 11 times 16, so you do the math, 176. The total number should be 342, okay? That means 342 grams of sugar, which is a third of a kilogram, basically. More than half a pound of sugar is this many, Avogadro's number. See the difference between them? How this is represented? So more than half a pound of sugar will contain about 12 grams, which is a small quantity of carbon, okay? Or 32 grams of air, oxygen. And that is because of the math number in there in the formulas. So now we have to be mindful of this number to try to see how much. So if I take 342 grams of sugar and put it in water, and if that would be the concentration in moles. So I have in this case 1 mole of sugar inside that water. So I can express the concentration in here instead of expressing at 342 grams per whatever in that liter, then I would say, no, I have actually 1 mole. So I can use the concentration in a molar number. Okay, again, in here we're going just to the example of moles. How many grams of water, H2O, are in 2 moles? Well, in 1 mole, you have 2 times 1, which is 2, plus 16, that's 18. So you have 18 grams in 1 mole, but you have 2 moles, 2 times 16, that should be 2 times 18, because 2 times 1, that's 2 plus 16, that's 18. 2 times 18 is 36, so the correct answer is 36. So molarity is a unit of concentration expressed in moles solute per liter of a solution. So that is one way of expressing the, so in this case, it's a number of moles per unit volume. Okay. So that is the molarity. That's one way of expressing the concentration. How many moles can you put in a liter before it becomes basically saturated? That's a question. Okay. On the other side, you have the ppm, or parts per million. So in this case, what we're saying in here is that how many parts of a solute you have for 1 million parts of a solution. So that's another way of also expressing it, usually for when the concentration is so sensitive to small numbers, small variations, where the mole molarity becomes too big. Then in this case, we use the ppm, parts per million. Okay. So that is also another way of expressing it. So basically, if we go back to the original example of sugar, then in this case, how many one molecule of sugar, which is that C12H22O11, how many of that sucrose you have in 1 million molecules of H2O? So you can use that concentration also. Again, each one of them has its own applications, and you can convert from one to the other if you know the structure, the chemical structure of the element to go from one part to the other. Okay. So again, solubility is the ability of a solute to dissolve in a solvent, and that is temperature sensitive. It depends on the temperature. Okay. The higher the temperature, the solubility increases. Okay. The solubility increases in this case, meaning that if I lower the temperature, the solubility starts to decrease with it. So that means that whatever I already have in the material starts to deposit in the bottom. Okay, I don't need a lot. So the saturation can be reached much quicker at lower temperatures than at higher temperatures. So that's why, for example, water that is cooler than water that is hotter will have more oxygen concentration per liter than one that is warmer. So if you increase the temperature of water, it starts to become poorer and poorer in oxygen, I'm sorry. Okay, so this is a property of the solubility. Okay, here is an example. So you have a saturation, for example, at 100 degrees Celsius. As you lower the temperature, because the concentration in here starts to go less and less. So in this case, of course, in here, this is not some elements, for example, like sodium, salt, hardly doesn't change, but this is atypical. Typical behavior is that the concentration in here will, or the solubility in here will increase, will require more. Okay, so the same thing in here. What I'm saying in here is that there is a deposition in this case, precipitation in this case of the solution because of the fact that this number will lower the solubility when you decrease the temperature, in which case you have an excess that needs to be disposed of, and it's going to precipitate in the bottom. So this is an interesting, the amount of oxygen O2 dissolved within the water of the Arctic Ocean is greater, about equal to or less than the amount of oxygen dissolved in tropical waters. As a matter of fact, it should be the concentration in this case should be greater because the solubility in this case is less. Okay, by mass, water is 88.8% oxygen. So why can't we breathe it? Okay, let's look at the map in here. Where is my pen? So what we have in this case is we have 2 grams of hydrogen and we have 16 grams of oxygen. And the total mass is 18 grams. So what you do in this case is you take 16 and you divide it by 18, and it's going to be 0.888, and it's repeating. So at some point it's going to be rounded to 9. So it's 88.8% when you multiply this by 100. Okay, so you ask yourself, water is mainly oxygen. Why can't we breathe it? And that is because it's a different chemical structure. The water we breathe is actually O2, not H2O. And this is the same challenge that we have, for example, for the Mars missions, because on Mars, it's CO2, actually. Carbon dioxide is mainly the atmosphere of Mars. There is hardly anything else other than carbon dioxide. So what MOXIE, if you guys were following the news with MOXIE for the Perseverance, which was successful in converting this carbon dioxide in carbon monoxide, plus of course oxygen. Of course, the chemical reaction is not properly balanced. You really need to have to balance it. So you have to have what, 2 times, yeah. Okay. So for each 2 carbon dioxide molecules, you end up with 2 carbon monoxide plus an O2 in this case, and this equation should be balanced now, okay? But that's how MOXIE worked. I know that when we were in the meeting, at least some of you were in on February 18th, when we were talking about this component, this model of the Mars lander, and I think Dr. Stanley was there with us, and he was wondering why do they do this process instead of other chemical processes. I don't know honestly, but it seems like that was the most efficient way of doing it. And that is basically how they did. And it was successful. They did generate O2 out of carbon dioxide in Mars. Of course, on Earth, you can do it. It's a very expensive and very dumb idea to do it that way, but that's basically how you do it. Especially CO2 is not necessarily, CO is not necessarily a good byproduct out of it, but you need oxygen. You need oxygen to basically for future missions, so that the whatever you send in there, so that it can return back, and combine that with hydrogen for fusion for chemical reaction, so that it can escape the pull of gravity of Mars and basically return to the orbiter, so that it comes back to Earth. So that is again a sign point, because it's similar to the same challenge in here. The question is asking about water, and it could very well be asked about the this carbon dioxide, because in carbon dioxide, what you have in here, you have 12 plus 2 times 16. So that is equal to 44 grams. And you have 32 out of 44. So if I do the math in here quickly, do I have a calculator? No, I don't. So it's going to be what? 44, I'm sorry, not 44. 32 divided by 44. According to my calculation, is 73%, okay? So it's still 73% of the atmosphere of Mars is oxygen. Actually, if you look at it that way, there is more oxygen on Mars than on supposedly O2 on Earth, because O2 is only about 27% the one that we breathe. So, and that is the reason why, again, because it's not coming in the pure form. The one that we breathe is the O2. Make sense? Okay, so then this is the discussion point that I want you really guys to think about. This, I think the MOXIE model of Mars. I want you to guys really look at this one in here and see the latest news from Perseverance on MOXIE model. Okay, so that's at least to keep up with that thing that we started way back in when we started this class. Although the question has to do with water in here, but similar. Okay. Soaps and detergents have polar and non-polar properties. So basically, it's a long molecule, and one side it's polar. Basically, it's an ionic structure, so that it has capabilities of attaching itself. So there is an O plus and O minus, or O minus and O plus, I should say. And then, so if you have an oxygen in this case, and you have a hydrogen that is depleted of a charge, and I'm sorry, positive. A hydrogen that is positive in here, depleted of its electron, and there is the 2 negatives in here. So it's going to be attach itself to the water. On the other side, it's going to induce a dipolar induced dipole basically interaction with the dirt that you have in here and attach itself to the grime. And you don't have just one, you have a lot of them. So the work of all of them, they use the water to dispose of the grime, to get rid of it, and basically that's how the process works. Okay? So if you are in the detergent business or soap business, that's what you do. You have to make sure that your chemical structure has this of your detergent has these properties. If it does, you test it, and if it works, then you're going to be able to sell it and bottle it and sell it and use it for that. So a non-polar part attracts to the grime, and a polar part attracts to the water. This is basically how it looks like. Okay, it looks ugly, doesn't it? And so is dirt. Okay, and that's how basically, so there is no polar in here component in here, but it's an induced polarity. So that's basically an induced binding in here. Okay, so which one is the correct answer? It's this one. Okay, hard water, the one that is actually in some households, has this high concentration of calcium and magnesium ions that start to deposit and basically start to form usually in the pipes and start to block and clog the pipes themselves, and it's a problem. So what they do in this case, what you really want to do is soften it. In other words, get rid of those ions of both magnesium and calcium. If you do that, then the water is softened so that now it can flow and the pipes can be cleared again. So this is an undesirable effect. You don't want that. So it clogs the pipes and lowers the cleaning action of soaps and detergents. That is basically what the problem with it. So, and then it forms the soap scum in here. So what you need in this case is detergents to remove these ions from it, okay? Some places what they have, they actually pump this detergent into the pipes, into the water, especially for the shower and other places, so that it stays unclogged and works fine. Okay, again, they're attracted because of, again, those are ions, and this is a polar the detergent, and it attracts itself to it, and then all of a sudden you have you can remove them from the solution in there. Some homes contain water softening units, actually in homes too, okay? And these are basically, they attract them and they get rid of them, and the water that comes out from the other end is a lot better. Purification of water is actually, you have to also do that. So it goes through a lot of stages. The first one is, of course, you have to get rid of the harmful stuff in it by removing the bacteria and the particles from it. And then actually getting rid of them. And once you get rid of them, usually you go through the process because it still smells. So you need to get rid of that smell and make it into a desirable form so that you can use it for agriculture or use it for irrigation or use it for landscaping, or not out of the realm of the possibility it becomes drinkable again, okay? So here is the process. So this is impurities in water. Again, those are usually non-homogeneous, heterogeneous mixtures. So what you do in this case, you add the aluminum sulfate that can grow, and the minute they're attaching itself to this dirt, and once it does, then it's going to deposit to the bottom and precipitates to the bottom, and now you have clear separation of the two, okay? Then it's aerated to improve the taste and the smell, okay? At the end, you need to kill whatever, so it's disinfected using either chlorine or ozone to get rid of whatever basically microscopic bacteria that is left in it, and now it becomes good, okay? Which of the following is not a method of disinfecting? So all of this are disinfections, except the aeration, just to improve the smell and the taste, okay? Purification of water, you can take water from the oceans and actually convert it into a drinkable water. Okay, through a processes of desalination. So you remove the salt from it, basically, that's what it is. There are two different methods, basically, either through distillation, which involves heating the water, increasing its temperature. So when you increase its temperature, it rises, it evaporates. So you need to collect the evaporated water in this case, which is pure water, but then collect it in another place so that you can use it later on, lower its temperature, and now it becomes pure water that you can use basically for whatever purposes water is used, okay? And of course, the salt will stay in the bottom. So that's really one way. The other process involves something called reverse osmosis. So what osmosis is, you take two different, basically, you take the water that has salt in it, and you take another water that is pure, and you separate them between with a material that has very, very small, basically porous structure, so that it allows for the water to move from one way to the other, and not the salt or the big molecules in this case. So what's going on in this case? Because on one side of the water, if you take the same amounts of them, it has a lot of salt in it. So it's poor in water, high in salt, and the other one is the opposite. It has high water. So water in this case will tend to move from one side to the other to balance the concentration of water. Because on one side you have a lot of water, and the other side you have a lot less water. So it's going to move from the pure side actually to where the salt is, to lower the concentration of the salt. And this will keep on moving until the actual volume of the salty water starts to increase. But now you have a problem. You have a difference in pressure, because even though one has moved to the other side, so now you have a higher level on one side and lower level to the other side. Now there is an imbalance. There is a difference in pressure between the two sides. And that is the osmotic pressure in this case, responsible, among other things, for how salt is used actually in the bloodstream and actually in the cells, to basically transport liquids and fluids and foods and all of these things. So you have an imbalance in this pressure that will stop the migration of the water from one side to the other, from the pure side to the impure side. Of course, you don't want that. What you want to reverse the process. You want actually more pure water to move, more water to move to the pure side. So what you do in this case, you use mechanical ways to push the water against the way it's supposed to act, against the osmotic pressure, so that there is more of the pure water and less of the saline water. So that's why it's called reverse osmosis. It's the opposite of what's supposed to happen naturally. And in this case, you end up with more pure water. So those are both processes. Both of them cost energy, though. The first one, in terms of the temperature that you have to boil the water for. So it's not a cheap operation. It requires energy, it requires engineering, it requires a lot of work. And you would want to make it into an industrial operation, because you don't want to create just 1 liter. You would want to have a lot of it. So that's one thing. The other one also would cost energy, because you have to really apply pressure against one side to really cause it to move in the opposite direction, so that you will have this reverse osmosis. And that too can present a challenge in terms of the engineering also, if you would want to make it in terms of an industrial operation. So both of them are costly. Which one you prefer depending on where you are in the world and depending on what you really want to achieve from it. Okay, again, here is the structure. So this water that you see in the bottle here is the pure water that is being collected in this case. So it uses in this case apparently just the normal sun. So the sun is heating the water in here. The radiation is going through. When it's trapped by the water in this case, the water absorbs this radiation and it becomes hotter and hotter. So it actually tries to get rid of that temperature through emitting it back, but it's going to be in a lower wavelength, a shorter wavelength, longer wavelength, I should say, lower frequency. The glass acts, if you guys remember from the greenhouse effect, it acts as actually an opaque material. It does not allow for a long wavelength radiation, infrared radiation, to be to be transported to the other side. So it actually traps heat in here, so it becomes hotter and hotter. So the increase in this case will be hotter, higher and higher, and then the water starts to evaporate because you reach temperature of 100 degrees Celsius, where the water actually starts to evaporate and starts to collect along the glass. If you tilt it just enough, like in this case, it's tilted and then it's collected in here. This is useful for creating what? How many gallons is this one? It's probably not even a full gallon. But if you really want it to be an industrial operation, you really have to come up with a lot better mechanism than this one to really make it operate. So it's a very costly operation, okay? Here is the osmosis, the one that I was talking about earlier. So if you put this is a sub-microscopic pore. That means it has to be just the right size to allow for the water to go from one side to the other, but not the bigger molecules in this case, okay? So under normal operation, the fresh water will move from here to there to balance the pressure, to balance basically the concentration, I should say, not the pressure. So in this case, there will be a pressure that will be created. So if you put them next to one another, the water starts to flow up to a point where this pressure becomes too high now, because you have this extra weight of the water, of the salty water, then this much, and that is the osmotic pressure. So if you reach that point, there is equilibrium and there is nothing that you can do about. So what you do in this case, if you want to reverse a process, you have to apply an external pressure. You have to actually do work in here to push the water, the same water, in the opposite direction. And now you end up with more fresh water than what you started with, okay? And then you can continue with the process again and again and again until basically you take more of this. Now it becomes so highly concentrated that probably you need to get rid of that salt or do something with it, okay? Same thing in here. You have to really dispose of that salt too, that forms, because it's a challenge too. So both of them represent their unique engineering challenges trying to build them, but they are feasible in a sense, okay? Wastewater, you can use cleaning to remove the large insoluble items in it. So, and then primary treatment allows smaller insoluble items to settle in the bottom or rise to the top until you separate them. Secondary treatment aerates the water and allows finer particles to settle for removal. And at the end, tertiary treatment filters the water. And at the end, you will have the water that you can clear. And this is basically the sewage, the intake, and at the end you have a water that at the end. Look at the solid, the waste at the end, okay? If you have seen some of those, what do you call them? Septic tanks that they are used, these are not different than that, okay? You can actually boil them and separate the hard part from the, until you get the water again treated and it's used for later uses for irrigation or other things that are needed for that. Anyway, the chapter was kind of light a little bit, so I'm glad that it is, okay? So unless you guys have any question, I'm gonna see you guys on Thursday to discuss chapter 17, okay, which should be on Canvas. And hopefully we'll finish all of the materials before the time.
Professor?
Yes.
I have a question. So it was just to write about the Mars, Perseverance, and Moxie?
Yes, as related to that question in there, okay?
Okay, thank you.
Thank you. Okay, thank you guys. I'll see you. Thank you, Thame. Thank you, Tanner, Corin, everybody. Let me stop the recording first. Where is the... Okay, how do I do that? Oh, there it is.